Okay, next question to go through is page 59. Okay, now if you now look at the question, they mentioned to you something similar to the question before. State a similarity and a difference between the fields of force produced by an isolated point charge and an isolated point mass. This is actually the same question that we've just done. So I don't think this one requires much explanation. You can actually just use back the same answer from before, where you say that both field lines are radial. They follow an inverse square variation. Okay, either they're radial or they have an inverse square variation. And then as for the difference, the direction of your field is always towards the mass for gravitational field, and the direction can either be towards or away from the charge for electric field, because this depends on the sign of the charge that you are considering. Okay, so this one should be okay, no issues here. Then after that, you look at part B. Again, it kind of looks the same as the first question that we just did. Here they tell you that you have an isolated solid metal sphere A of radius R with a charge of positive Q. Then from there, they mention that there's a point P, a distance of 2R from the surface of your sphere. All right. Determine an expression that includes the term big R and big Q for the electric field strength E at point P. Okay. So right now you want to use this equation. All right. This is the electric field strength. All right. So electric field strength, this one, just now I did mention to you, this one is only for point charges. I need to re-emphasize this point here. Just let me write it here. This one is only for point charges. Okay. So you see this sphere is considered to be a point charge because it's a sphere. And then when you have a point P here, this one you can consider, if you wanted to test this point, you would just put a positive test charge, which is also again a point charge now. So you can actually use this equation, E equals to 1 over 4 pi epsilon naught Q over R squared directly. Okay, so here I did mention to you your R is actually usually the distance between the charge itself and the point considered. So here, if you're talking about the field strength at point E, this part here, your R is actually this one, distance between your charge to the point that you consider. So this R, if you want to express it in terms of big R, is actually equals to 3R. Okay. So you want to use equation E equals to 1 over 4 pi epsilon naught Q over R squared. Your small r is actually 3R. But don't forget to square it so that eventually you get 36. All right. Your final equation would be Q over 36 pi epsilon naught R squared. This one would be your final answer. All right, so this one is pretty straightforward. Now, after that is where it kind of gets a bit complicated. This time they're going to add another charge. Here in part C, they mentioned to you that a second identical solid metal sphere B is now placed near sphere A. The centers of the spheres are separated by a distance of 6R as shown. And now they say that point P is actually midway between spheres A and B. It is right in the middle between the two spheres. So here they further mention to you that sphere B has a charge of negative Q. So explain why the magnitude of the electric field strength at P is given by the sum of the magnitudes of the field strengths due to each sphere. Okay. So how do you go about doing this? Let me just write out some important information. Fe is 1 over 4 pi epsilon naught QQ over R squared. And then after that, E is 1 over 4 pi epsilon naught Q over R squared. Okay. So this one, the important thing to note is that they are only for point charges. All right. Okay, so now if you're talking about your charge A and charge B, sphere A and sphere B, sphere A is positive, sphere B is negative. All right. So if you're talking about opposite sign charges, like this one here, you're having a positive charge here with its own electric field like this. If I just consider them individually, you have one positive test charge here. So you have one positive charge, isolated charge, and then you have one negative isolated charge here whose electric field is like this. They are both supposed to be radial if they're far apart. But what if you bring them close to each other? So you bring them close to each other, the idea is that the field around this part and the field around this part would tend to overlap with each other in this region here. Okay, so it will form a new electric field. Okay, so when you want to talk about whatever is inside this region here, if you say you want to find out the electric force, you want to find out the electric field strength, it's usually the combination of the two individual charges added together. Okay, so in your case now, because if you're dealing with field strength or force, they are vectors. If you want to add them up together, you have to consider direction. Okay, so the idea here is that if I have a positive charge and a negative charge here like this, and there's a point P right in the center, right over here, there's a point P here. Consider that you put a positive test charge here to test the field. All right. So if this one is sphere A and this one is sphere B, whatever field strength that you have at point P is actually due to A and B combined together at that point. So you have to consider the individual effects due to A and B first. So if you consider the effects of sphere A on the positive test charge at P, the direction of your electric force on the test charge would obviously be towards the right. This one will be the electric force due to A. But at the same time, your electric field strength due to A will also be in the same direction. Okay, it will be towards the right. Now, if you then consider the electric field strength due to sphere B, meaning to say you consider like this right now, this is negative, this is positive, so obviously your electric force and hence electric field strength due to B alone would be towards the left. Your FB will be towards the, sorry, not towards the left, my mistake. Because it's positive, negative, the positive test charge will be attracted towards the negative charge, right? So your electric force due to B will be towards the right. Your electric field strength due to B will also be towards the right. Okay, so here the conclusion then would be that your field strengths are always in the same direction. There's no opposite direction, so there's no negative to consider. So in your case here, your EP, the electric field strength at P, which is essentially your resulting net, which is your resulting field strength, it will actually be EA plus with EB. Okay, it will just be that. Now, if you then want to expand it a bit further, it will become this expression here. 1 over 4 pi epsilon naught QA over RA square plus 1 over 4 pi epsilon naught QB over RB square, where your RA is the distance between sphere A and your test charge, and your RB is the distance between your sphere B and your test charge. So let me just try to draw them out. This is where all your, you see a lot of writings on the screen. Okay, so this one, let me just use different colors to highlight it to you. This one, probably I'll just use this color then, blue. Okay, this one is your RB. Okay, this one is not a nice color to use. We'll use purple then. Okay, this is your RB. Okay, right. So this one came from this one. Okay, this one also came from this one. It's just that you're applying it for a pair of point charges. You see, when you use E equals to 1 over 4 pi epsilon naught Q over R squared, this one is only applicable for point charges, specifically 2-point charges, actually. 2-point charges. In your case, if you look at your diagram right now, there's actually a pair of point charges here. This one is namely sphere A and your test charge. So you can use E equals to 1 over 4 pi epsilon naught Q over R squared. And then you look at the other part of your diagram, this is also another pair of point charges. So you therefore can use E equals to 1 over 4 pi epsilon naught Q over R squared. Okay, so your 2-point charges here is usually the main charge and your test charge. That's why I can use EA plus EB here and expand it to what you see here. All right, so this one just bear that in mind. Then after that, I go back to the question. So the question is really asking you right now, why is it that the magnitude of your field strength at P, the sum of the magnitudes of the field strength due to each sphere? In other words, they're asking you, why is it that EP is actually EA plus EB? The reason is because in the first place, your field strengths due to each sphere are in the same direction. If you look at the field strength due to A, is towards the right. If you look at the field strength due to B, it's also towards the right. So that's why you can just add them up together. That is the understanding here. All right. Then after that, you move on to part 2. Okay, part 2, this one is the one that sometimes causes confusion with a lot of people. So you look at part 2, they mentioned to you that electric field strength at P due to the charged metal spheres is not in practice equals to 2E, where E is the electric field strength determined in B earlier. Okay, so they're asking you right now to explain if before this one I think I have to write on the left hand side. If before this, if you consider sphere A and a positive test charge, this one having distance of 3r, r equals to 3r, you found out the electric field strength as E, some value lah. And they told you that your electric field strength was Q over 36 pi epsilon naught r squared, right? So they just tell you the E here is the field strength determined in B. Okay, so this was what you found earlier when you consider the test just sphere A alone. Right now they are asking you, when you have sphere A and sphere B together, because you say that EA was E earlier, EB by right should also be E. So shouldn't EP be equals to 2E? That's what they're asking you right now. Okay. The electric field strength at point P due to the charged metal spheres is not in practice equals to 2E. So you need to explain why is it not equals to 2E. Because you can see from here, because they mentioned that your point P is midway between spheres N and B. Okay, so you actually have some sort of symmetry here. What do I mean by that is, if you look at sphere A, you have a distance of 3r, right? If you look at just sphere B alone to your point P, this one is your point P just now, it's actually symmetrical. It's actually the same. If you have a negative test charge here, this one is sphere B, and then you again have point P right over here, again a distance of 3r away, because the question really did mention your P is actually midway between the two spheres. I think it's easier to see from here. This one was 3r, and then this one is also 3r. So if you had considered just this one alone, they say that EA was E. So you consider this one, by right EB should also be E. Okay, so if EP is equals to EA plus EB, shouldn't this mean E plus E equals to 2E? That is the understanding here. So the question now is saying, why is it that this is not the case in real life? Why is it not the 2E in practice, in reality? Okay, so this one, you need to kind of explain it in this manner here. All right. Now, in the first place, it might probably be easier if I just explain it this way first. You see, when I say EP is equals to EA plus EB, and then subsequently I get this equation here, these equations were under the assumption that you have point charges. Okay, this was under the assumption that you have point charges between A and test charge and B and test charge. You use that equation under the assumption that your sphere A and B itself were point charges and your test charge was point charges. So the only way that you will not get this one is if your assumption that they are point charges is invalid or wrong. Okay, because how you did this is that you're assuming that all your charges are point charges. So you assume that they're all point charges, you would get 2E. So the question is asking you right now to explain why is it not 2E. So you have to kind of explain why are they not point charges. That will tell you then why they are not equals to 2E. Okay, so to explain why sphere A and B are not point charges, you could say any one of these answers. The charges on the sphere attract or affect each other, so therefore they're no longer point charges, or the charge distribution on each sphere is distorted by the other sphere, so they're no longer point charges, or because the charges on the spheres themselves move, so they're also not considered point charges. So if you have any one of these, this will tell you your spheres are not point charges. Therefore, this one would be invalid, which would then tell you why this one cannot be 2E. Okay, so these are, if anything, maybe I should write this here. These are, in other words, reasons why something cannot be a point charge. Okay, this is something like reasons why an object is not a point charge. Okay, in the lesson that I did with you previously, I did it the other way around. I told you what can you assume as point charge, right? That time I mentioned to you, if it's a charge sphere, or if the separation is very large, wait, let me just erase this. If I tell you that the separation is very large, then you can assume as point charge. This was what I explained to you in the first lesson. Under what circumstances can you assume something as point charge? It must be a sphere. It must have very large separation. But this question is kind of like doing it the other way around. They're asking you to somehow explain to them why can you not assume them to be as point charges, which would be either one of these three. Okay, so that's for this question, right? So hopefully this is okay. Then I will move on to another different question, right? Can you guys just have a look at page 26? There's something further that I need to kind of explain from all these things that I've just drawn here. Okay, so stack columns law, this one you can just copy it from your notes. The one I want to discuss with you specifically now is B. Now you have two charged metal spheres inside a vacuum. Okay, there are two charged metal spheres A and B that are situated inside a vacuum as illustrated in figure 6.1. The shortest distance between the surfaces of the spheres is 6 centimeter. And then they then mention to you that a movable point P lies along the line joining the centers of the two spheres, a distance x from the surface of sphere A. The variation with distance x of the electric field strength E at point P is as shown in the figure here. Okay, this is what you have. So you again have sphere A, sphere B. What you would easily understand is that sphere A has its own electric field. Sphere B again has its own electric field. You move them close to each other, they are going to combine in the region between the two field, in the region between the two spheres to give you a new electric field. So what you have here in the graph is actually talking to you about the electric field strength in this region, the resulting electric field strength. This is actually your E net, resulting electric field strength with distance x. Your distance x is measured from sphere A. Okay, so you notice as distance x increases, this is how your field strength versus distance looks like. Okay, so from there, the question then mentioned this. If you look at the next page, they're asking you to explain from that figure that you have whether the two spheres actually have the same sign of charge or opposite sign of charge. Okay, now this kind of question comes up quite often. Actually, they will give you some sort of electric field strength versus distance graph or potential versus distance graph, and then they ask you to deduce whether the two spheres have same sign or opposite sign, meaning to say whether they're positive, or positive, negative. So you are supposed to deduce that from the graph itself, from looking at the graph itself. Okay, so in your case, how do I know it's positive, negative, or negative, positive? It's like, well, how do I know it's positive, negative, or just positive, positive? So we consider some cases, there's really only two cases, either same sign or opposite sign, right? So the opposite sign one, I actually already did it here from the previous question. We will consider the case where you have same sign charge. So this one will again be some very lengthy explanation. This one, if say for example, you have sign charge, okay, this is same sign charge, where I assume that this one is positive and positive, okay. So in my case, sphere A again is positive. Sphere B is also positive. Okay. So if I'm interested at a particular point P in the region between the charges, let's say that point is right over here. This is my point P. I want to test that field at that point. I will put the positive test charge. Okay, so if I now want to find out the electric field strength EP at this point, or the resulting field strength E net, as mentioned, you need to consider the individual effects of the spheres. You need to consider the effect due to sphere A. You need to consider the effect due to sphere B individually on your positive test charge here. All right. So if you try to consider the effects individually, say for sphere A, you come to this conclusion that because they're both positively charged, the electric force on the test charge is towards the right, and so would the field strength due to the sphere A. So your FA and EA is towards the right. But then if you now consider the effects due to sphere B on your positive test charge, because these are positive, they are repulsive by nature, this would mean that your electric force due to B and subsequently your electric field strength due to B will be towards the left. This one will be opposite direction. So since you're talking about field strength, which is a vector, anything which has an opposite direction normally would be given a negative sign. So in your case, EP is actually going to be, okay, maybe I use a more striking color here. Okay, I use yellow again. Here you would say EP is actually going to be EA plus with negative EB. Okay, this one here because opposite direction. It's different than the one before. You have no negative because both were acting in the same direction. Okay, so here now, if you want to expand it, this again becomes 1 over 4 pi epsilon naught QA over RA square plus 1 over 4 pi epsilon naught QB over RB square, where your RA is this and your RB is this. Okay, so that's one thing to note. So from there, if you just look at this equation, there will be some things that you can actually deduce. Because you see, EA is positive, EB is negative, there could come a point where EA and EB are equal and opposite to each other. Because you see, when your X is increasing, this one is your X is measured from your sphere A. This one I have to kind of draw it here. Just let me try and find a suitable color. Your X is measured from the left-hand side from your sphere A, okay? Consider this now. If your X is increasing, wouldn't your RA, your X determines where your point P is, okay? If X was here, this is where your point P is. If X was here, this is where your point P is, okay? So your X determines where your point P is, all right? Just bear that in mind. So if your X is increasing, wouldn't this tell you that RA is increasing and then RB is decreasing? Because you're basically shifting your positive test charge from here to here. So your RA obviously would increase, right? Whereas your RB would be decreasing. So what does this cause to your field strength? If you look at the equation at the top here just now, if everything else remains constant, E is actually inversely proportional to R squared, isn't it? So the moment you have R increase, your E drops. When your R drops, your E increase. So translating it to each of your sphere A and sphere B, this is what you get. Your RA increase, your EB should decrease. Your RB decrease, your EB should increase. So when you go further and further away towards the right, when X increases, you have a case where sorry, this one I wrote it wrongly. This is EA, right? Okay. RA increase, EA drops. Sorry, I got that mistaken. Okay, so if you go towards the right, your EA is dropping and then your EB is increasing, isn't it? So you'll come to a point where EB is going to be more than EA. Okay, your E net is going to be towards the left. Because you see, EA is towards the right, EB is towards the left, right? So if you go further and further away towards the right, your EB is becoming larger and larger, your EA is becoming smaller and smaller. So obviously your EB will be larger than your EA. Your net electric field strength will be towards the left itself, following the direction of field strength due to B. Okay, so just bear that in mind. Then after that, what happens if I say the X decreases? If my X decreases, this would mean that RA drops, so EA increases. And then conversely, RB would increase, so that EB drops. So in my case here, if I consider this would mean that EA is now more than EB. So that my ENet is actually towards the right. Okay. So then if you consider these two effects, there's EB more than EA, so that ENet is towards the left. There's EA more than EB, so that ENet is towards the right. There will be a point in between where EA is equals to EB. So you consider these two facts here. Somewhere in between these two, EA will be equals to EB, so that ENet is equals to 0. Okay, so let's just say for our discussion here, we say that point is right over here. This point here is where ENet equals to 0, right at this point here. Okay, so if I go more towards the right hand side right now, my ENet would be towards the left. Okay, maybe I draw it at the top here. Now this one is one part here. Okay, this one is ENet 0. What if I go towards the left or right of that point where ENet is 0? If say I go towards the right hand side, I'm expecting to see something like this. This part here is where ENet is towards the left, because EB more than EA. Okay, this is because EB more than EA. EB more than EA. Then if I go towards the left hand side, this one will be ENet towards the right, because EA is more than EB. Okay, so these are certain points to take note of. This one and this one. Okay, so now the thing is that if I then want to draw a graph of field strength versus distance, this is the thing that I wanted to explain how the graph shape came about. If you want to plot a graph of, say, field strength versus distance, the ENet versus distance, E versus X, by right, you're supposed to get a graph shape that looks like this. Maybe I erase this one so that you don't get confused. Your field strength versus distance will be something that looks like this. Okay, where you see that this part here is where ENet equals to 0. This part here is where ENet is actually towards the right. This part here is where ENet is towards the left. Okay. Another way people can look at it is this way lah. This is positive ENet. This one is towards the right. This one is negative ENet. You're going towards the left. You have opposite signs. Okay. And then this part here is ENet equals to 0. So if you're talking about a charge with same sign, this is the graph you expect to see. Why do you have a positive and negative field strength? Is because one becomes larger than the other eventually. And then eventually you also notice there will be one point where your ENet is 0. So this graph that you have is actually this graph here. You see, there are two different directions of your ENet, and then there's an ENet being 0 in the center. This is actually already implying to you that you have same sign or charge. Okay. In the marking scheme, the answer is pretty simple, but why do they say that? It's actually based on all these things that I've just written here. This one is June 17 P42, right? Let me just open up the answer. You're really supposed to only say something like this now in the answer. Okay. Okay, this one I cannot. The problem with using Zoom is that I cannot just simply erase off certain things. Okay, right. So let me just erase off the things that I just wrote in the center here. All right. So if you want to explain whether the spheres have the same sign of charge or opposite sign of charge, there's generally 3 points to it. You need to choose only 2. So the first point you can say is that near to each sphere, the electric fields are in opposite directions because you see a positive and negative there. So that kind of really implies to you that you must have same sign of charge. Or you can also say this. At the point between the 2 spheres, the resulting field strength is 0 because the fields must be equal and opposite there. So these 2, you need to choose one. Choose one. Because either one of these will explain to you that your spheres actually have same sign of charge. Okay? This is where your other point comes from. So choose one point. You saying same sign of charge is another point. Okay? This is how you deduce from your field strength versus distance graph. You either identify the fact that there are 2 different field directions, therefore they must be same sign, or you identify that there is a 0 field strength in the middle somewhere, so it must be same sign. Okay? Just by reading this by itself usually doesn't make much sense. You have to kind of relate it to the explanation and the diagram here. Only then would it kind of make sense to you. All right. Okay, so this one is for same sign of charge. Then what about if you have opposite sign charge? So let me just draw something here. Just now I told you that for your field strength versus distance, your graph shape will ideally look like this. Okay, so as a summary, just kind of look at this now. This part, this one is opposite field strength, therefore same sign of charge. This is one way in which you can kind of deduce out your answer. You always look at these 2 points. Opposite field strength means same sign of charge. Or you can always look at this point. E net equals 0. Fields are opposite direction. Therefore, same sign of charge. This one is you just by looking at the diagram now. Then you can relate it to the one above. Okay. Now, back to the part where you're talking about opposite sign charge, how would the graph look like? Okay, now for the opposite sign charge that you have here, the EP equals to EA plus EB, there's actually 2 conclusions that you can actually get from here. Number 1, your EP will never be 0 because it's positive plus with positive. If you have 2 positive numbers added up together, you will never ever get 0 unless you have a negative for one of them, right? So you see EA plus EB is both positive, both of them will never be 0. And then another thing to also note is that they will also never be negative. If you keep adding up positive values together, how is it possible you will get negative? It's just not possible, right? So if you are talking about the field strength versus distance graph for opposite sign charges, it will look something like this. Okay, this one, let me just redraw this. For field strength versus distance graph, it will look something like this. There is no part where it will go to 0. There is no part where it will go to negative. Okay, so this is your graph shape that you expect to see. So if let's say you're given a field strength versus distance graph like this, and then they again ask you to explain whether the two spheres have the same or opposite sign charge, your answer will more or less be the same. You will see right over here, you have same direction of field strength, same field strength direction. You have same field strength direction, therefore opposite sign charge. Okay, in your current case, this is the only answer you can say. Unlike this one here, you have two different ways to say that. Either you say it's opposite field strength seen near the spheres, so it's same sign of charge, or you say the field strength is 0 right in the middle somewhere, so the fields are opposite direction, therefore same sign of charge. But when it comes to the part where you have opposite sign charge, there's really only this that you can say. You notice that same field strength direction near the sphere, therefore you have opposite sign charge. Because you can also kind of see from here in the first place. Right? You see, if you always keep adding a field strength towards the right and then a field strength towards the right for A and B, there will never be a case where you suddenly get a opposite field strength direction towards the left, right? It will always be positive. Okay? So the fact you don't see an opposite sign already kind of already tells you that you do not have same sign of charge like this. There must be opposite sign like this. So that no matter what you do, it's always in the same direction when you add up your field strengths. Okay. Okay. So what's the difference between this graph that you have here versus another graph that you drawn earlier? We also draw field strength versus distance, but then I told you that graph looks like this, right? Remember this graph that we just drew? So what's the difference between this graph and this graph? Both are talking about field strength versus distance, but under what circumstances do they apply? So this one is just one thing I kind of need to explain to you. This one is usually for isolated point charge. Meaning to say, you have some sort of sphere. Okay, you have some sort of sphere like this. And then you measure your distance x from the center of the sphere. You find out what is the field strength at different points from the isolated point charge. Say this one is E1, this one is E2, and then this one is E3. So for that part I mentioned to you, this one you specifically use E equals to 1 over 4 pi epsilon naught Q over R square, right? So this one is for isolated point charge only. This diagram that you see here is only for isolated point charge. Okay? You actually have two charges here. Actually, if you go and consider your test charge put in. So when you, although I say it's isolated point charge, there's actually two charges, 2 point charges. If you consider your test charge that you use to test the isolated charge. So because it's 2 point charges, that's why I can just straight away use this equation. Then your graph looks like this now. Okay? But for the other graph, the one that you're seeing right over here, this one is usually for between two charges. Between two charges. If you look at this one, this diagram here, there was actually a sphere A right over here and a sphere B right over here, right? So you have sphere A and sphere B. So you get this graph shape when you are talking about the field strength between 2 point charges, not an isolated charge. Okay, so in this circumstance here, this graph line that you have the equation that it follows is actually this one here. It follows this one. EP is EA plus negative EB, then giving you this. That's how you got this particular graph shape in the first place. Okay, because it's for between two charges. But when you come across for isolated point charge, this one is just strictly speaking just this. Okay, so there's a difference sometimes that people get confused because sometimes they do the electric field question, they say they draw this, but then another question they somehow draw this. You need to be aware of the differences between those two. The first one is for isolated point charge. The second one is for between two charges. They tend to follow different equations, so that's why the graph shape is different. They're not the same. Okay, so far so good. Right, so back to the question just now that I was talking about, this question here. So if you look back at this particular question, there's one part that we haven't finished. All right, they mentioned to you in part 2 that a proton is at point P where x is equals to 5 centimeter. Use the data from figure 6.2 to determine the acceleration of the proton itself. So this one will be pretty straightforward. They now tell you at x equals to 5 centimeter, you have a proton there. What is the acceleration of that proton? So if you look at your diagram from before this one, they're asking you to look at x equals to 5 centimeter, which is this one. They're telling you right now at this point, you have a proton. Okay, so say for example, your sphere B is here, your sphere A is here. Okay, your sphere A is right over here. So at this distance 5 centimeter, your resulting electric field strength is actually some sort of negative value. It's actually negative 3 times 10 power 3. It's actually negative 3 times 10 power 3 lah. So your field strength is actually in this direction. Okay, this one is E equals to 3 times 10 power 3 volt per meter. So they want you to find out what is the acceleration of a proton that is placed at this point here. What is the acceleration A? Okay, so to do this, you need to remember certain things. E is Fe over Q. So that Fe is equals to QE. This is number one. When you're dealing with acceleration, you will always use F net equals to MA. In your case, your F net is actually equals to your Fe. So this one you need to sub in so that you get QE equals to MA, from which you can now find out what is A. You know what is your charge of your proton, you know what is your electric field strength, you know what is the mass of your proton, from which you can now find out what is A. So that's how you got your answer right over here. Okay. Here I did mention something similar. At x equals to 5, E is this value, so MA is equals to QE, A is QE over M. You just sum in the values, you will get your answer. Q is your charge of electron. Proton and electron carry the same magnitude of charge. It's 1.6 times 10 power minus 19. Your field strength is something you got from your question paper. Your mass, 1.67 times 10 power minus 27, is something you get from your data sheet. Specifically, the second page again. You see there's mass of proton here, 1.67 times 10 minus 27. You get it from there. Okay. So eventually you will get your answer as 2.87 times 10 power 11 meter per second square. Just like that. Part C you cannot do yet because it concerns electric potential. This is actually the next part of your electric field chapter. So you did it okay, then I move on to another question. This one Should be slightly easier now. Okay, so have a look at page 47. This one is actually June 19 P41. Okay, so state what is meant by electric field strength. Field strength is actually just force acting per unit positive charge. Nothing to it. It's just a simple definition question. And then now you look at part B. Part B, they're mentioning to you that you have 2 point charges A and B that are situated at a distance of 15 centimeters apart in a vacuum as illustrated. Point P lies on the line joining the charges and the distance x from charge A. This is point P, distance x from A. And then from here, they mention to you that the variation with distance x of the electric field strength E at point P is as shown here. Okay, so from there, they subsequently ask you, by reference to your direction of electric field, state and explain whether the charges A and B have the same or opposite signs. This is again the same question as before. Notice that it has been repeated again. They again want you to look at the graph and explain whether the charges or the signs are same or opposite. So you can either say that because the field changes directions, there's 2 opposite direction of field, thus the charges have same sign. Or you can say another different way. You can say that the field is 0 at a point between A and B, so the charges have same sign. Okay, so generally you normally single out either this point to explain that they have same sign, or this point where the field strength is 0 in order to explain that they have the same sign of charge. Okay, your answer is always either this or this. Okay, pick either one. Either you say they have opposite field directions, so same sign, or field is 0 at some point, so same sign. Okay, it's just 2 marks usually. Okay, then after that, go and look at part 2. For part 2, they mention statewide, although charge A is a point charge, the electric field strength between x 3 centimeter and 7 centimeter does not obey inverse square law. When they say does not obey inverse square law, they're really asking you this. This is your inverse square law. E is inversely proportional to R squared. They say right now, charge A is already stated to be a point charge. Why is it that between 3 to 7 centimeter, you do not obey an inverse square law? Meaning to say from here to here, why doesn't it obey an inverse square law? Why does the graph shape look like this? You see, if your graph is following an inverse square law like this one, it should rightly look like this. E versus R should be this. This is what we mean by following an inverse square law. But somehow your graph shape doesn't look like what you have above here, right? This is the actual one. This one is if it's following inverse square law. So the question is asking you, why doesn't it follow the inverse square law? Maybe I should write it here. This one is following inverse square law. Okay. This one would be following E equals to 1 over 4 pi epsilon naught Q over R squared. So the question is, why doesn't it follow this? Why does it follow something like this? Okay. So this one I also kind of did explain to you. The reason why your graph shape was like this in the first place is because it follows this equation here. That's why it doesn't follow inverse square law, because it's a something else right now. And the reason why it looks like this right now is because you had to consider that field due to A combines with field due to B to give you some sort of new resultant field in the middle. Okay, that's why the way you would calculate it is different now. All right, so if you want to now explain why, you can just very simply say the reason why it doesn't follow is because the field is actually the resultant of 2 fields now. Okay, whatever you have there between 3 centimeter to 7 centimeter is actually the resultant of 2 different fields. Okay. Or you can also say some other answers like the charge A is not isolated, it's not the only charge present, there's another charge B here. Or you say the field is due to two or both charges. It's actually related to point number one. Okay. So that's how you would answer this question. Okay, last one. Use figure 5.2 to determine the ratio of magnitude of charge A to magnitude of charge B. So usually for this kind of question, it actually kind of repeats itself quite a fair bit also, where you're supposed to find the ratio of the charges. So when you want to find the ratio of the charges from a certain graph, the easiest point to pick is usually the point where your E net is 0. Meaning to say on your graph, this one. This point here is where your E net is 0. This implies to you field due to A is equal and opposite to field due to B. Okay, so from there you can find the ratio of your charges already, where you say something like this. At x 10 centimeter, the fields due to A and B are equal or opposite to each other. EA will be equals to EB. So EA will be 1/4 pi epsilon naught QA over RA square. QB will be 1/4 pi epsilon naught QB over RB square. So you notice that your constants here actually don't matter, they cancel each other off. Eventually you will get QA to QB as RA square to RB square. So all you need to do now is to find out the values of RA and RB, take the ratio and square them. So this part here, you need to be careful a little because the graph that you have here is actually not really accurate. Yeah, what I mean by that is, say for example, your field strength is 0 at x equals to 10, right? At x equals to 10 centimeter. So what you want to find is RA and RB now. If say I tell you that this one is 10 centimeter, RA would be this one, which is actually 10 centimeter itself. RB would be this one, which would be 15 minus 10, giving you 5 centimeter. Okay, this is your RA and RB. Now you try to find RA and RB from your graph, you might get your values wrong for RB because of this. You see, if I erase this thing out for you, you may have thought that since this point here is where your E net is 0, this one is your RA equals to 10 centimeter, and then this one is your RB. But you notice this one is 14 minus 10. Is 4 centimeter. Is different than the one above, isn't it? This one is actually wrong because your graph, this graph here, I should mention, the graph is not drawn all the way to sphere B. It isn't the complete graph. So this graph is not drawn all the way to sphere B. That's why here your value is actually not really accurate. It's not 4 centimeter. If I continue drawing it, say up to here, you would have gotten RB as 5 centimeter. So you don't try to read it from this. You try to read it from the diagram above. Okay, your RA is 10 centimeter, your RB is 5 centimeter. So once you have that, this is what you get. Ratio of QA to QB is the ratio of RA square to RB square. It will be 10 squared to 5 squared, giving you 4.0. So this is your final answer. Okay.